Modern front-end web development can feel like trying to untangle an endless web of abstraction. We rely on frameworks, libraries, and build tools to manage thousands of moving parts, and it's easy to lose sight of what the browser is actually doing. This diagram shows the React front-end layer acting as the middleware for our logic. But underneath all of that complex React architecture, the real engine doing the work is the standard browser object model, or BOM. It's the native data structure you are actually programming. To prove this, we are going to build a working, minimal version of React from scratch, using nothing but native JavaScript APIs. We'll code a virtual DOM, wire up a reactive state store, and write a diffing engine to sync it all together. Let's call it MiniReact. When you master the underlying browser object model, you stop being trapped by framework-specific syntax. The tools that once looked like magic simply become manageable engineering patterns you can control. Step 1 is fixing our vocabulary. The BOM is the actual data structure inside the browser. The DOM is just the topology, the tree of HTML element objects hanging off the document node. A real BOM node is expensive to create and mutate. Walking through the live browser tree and changing elements in place takes serious computational power, and doing it constantly will drag down your app's performance. To avoid this, we create a virtual DOM. Instead of building browser nodes right away, we describe each node as a lightweight plain JavaScript object, holding its data in memory before it ever becomes a live element. We can model this by writing a simple JavaScript helper function called createElement. It takes 3 arguments: the element's type, its properties and events, and its nested children. It simply returns a plain object containing those fields. If you call this function to build a small UI and log it to the console, you'll see a complete topology of nodes. This entire structure exists safely and cheaply in memory. We haven't touched the live browser yet. Now we need to bridge the gap. A virtual DOM tree is useless until it is actually projected into the real browser window. We need an initial mount step. We do this by writing a render function. This function walks through our in-memory tree, and for every virtual node, it calls the native BOM APIs, like document.createElement for the node itself and setAttribute for its data, to build the physical layout. We also need to map our events. If our virtual node has a property like onClick, our function needs to slice off the on and convert the rest of the string to lowercase. This allows us to pass the standard click event into the browser's native addListener method. Finally, we instruct the browser to take this newly built tree and append it to an empty root div element inside our index.html file. By successfully rendering these elements, we have effectively built our own framework abstraction. We are driving the live browser interface entirely from our JavaScript data. But right now, this is just a static one-time render. It cannot respond if a user clicks a button or changes the data. We need state changes to automatically trigger a re-render. To solve this, we use the observer pattern. We write a createStore function. This acts as our reactive store. It holds the initial state, updates that state through a setState method, and registers a list of subscribers, the observers, that need to be notified whenever a change happens. Next, we wrap our initial mount logic inside an update function. When notified of a change, this function rebuilds the virtual DOM in memory, creates a new real DOM node, and swaps the old one out using the browser's replaceChild method. Let's wire this into a counter component. We bind our store's state to a virtual heading, attach setState to our increment and decrement buttons, and then subscribe our update function to the store. This flowchart illustrates the core loop that powers modern UI frameworks. The state changes, the observers are notified, the virtual DOM re-renders in memory, and the browser syncs to match. Our MVP works, but it contains a massive performance flaw. Every single time the state changes, we throw away the entire DOM tree and rebuild it from scratch. We solve this with reconciliation. We keep a copy of the old virtual DOM in memory and compare it against the new one. By calculating the exact differences, we only touch the specific parts of the live browser that actually changed. We implement this by writing a diff function. It walks down both trees simultaneously, checking if a node's type has shifted or if its raw text value has been updated. This diagram shows a schematic of the Chrome DevTools Elements panel. We update our application to use a new mountReconciled function. Instead of swapping the whole tree, it uses our diffing logic to only mutate the precise nodes flagged by the engine. Try it yourself. Open your browser's DevTools, watch the Elements panel, and click the counter. Only the text node inside the heading flashes purple. The surrounding buttons remain entirely untouched. That selective, surgical syncing of memory to the live browser is reconciliation. The true optimization engine of React is now completely demystified. By utilizing native BOM APIs, you have built the 3 foundational pillars of React from scratch: the virtual DOM to hold the layout, the observer pattern to manage reactive state, and the reconciliation diffing engine to keep it all highly optimized. Now that you have the foundation, try extending it. Architect a localized useState hook so individual components can own their state without relying on the global store. Or take on the challenge of adding keyed children to your diffing engine, allowing lists to reorder themselves by reusing existing nodes instead of destroying them. The next time you sit down to write code in a production React environment, the virtual DOM and hooks won't feel like a black box. They are simply clear, logical engineering patterns that you fully command.